accept. So give and take is always happening simultaneously. When someone is giving out something, whether it's a proton, hydrogen ion, or electron, there has to be someone out there that can take them in. Okay, so Bronsted-Lowry definition says a substance that can accept a hydrogen ion is a base. So examples of base, we can have hydroxide ion. Okay, hydroxide ion. We can have ammonia. Now, what is in common between these two? Well, if you draw the Lewis structure there, you have lone pair of electrons on oxygen, an atom with high electronegativity value. If you draw a Lewis structure for ammonia, you have a lone pair on the atom with high electronegativity value. So the key here, in order for something to qualify as a Bronsted-Lowry base, a Lewis structure indicates a base must have at least one lone pair of electrons in order to accept the proton. Now remember the proton, H+. It has an empty orbital, no electrons. Now if you have a lone pair of electrons, H+ come in, that lone pair of electron will be shared between the hydrogen and the atom with the high electronegativity value. You form the chemical bond there. Okay. Without the lone pair, they will not be able to accept that proton there. So this is how we define base. Okay. So the definition here is that now if you have ammonium NH4+, or if you draw the Lewis structure for NH4+, you ask why does it bear a positive number, a positive charge there? Well, ammonium is nitrogen is 5. Nitrogen is a group 5A, so 5 valence electron. 5, 6, 7, 8. Total of 8 valence electrons. All are accounted for. Now, if you bring in a proton, you get 8 protons here plus 1 more proton. So you get now 9 positive charges, only 8 electrons. You should bear a positive charge. So can ammonium act as a Bronsted-Lowry base then? Well, in this case, there is no lone pair of electrons. There's no way you can put another proton on this molecule or on this ion. It cannot be a Bronsted-Lowry base. So you got to know the definition. How we define the Bronsted-Lowry definition is one of the definitions. Then we have Lewis acid, Lewis base, Arrhenius definition, Arrhenius acid, and Arrhenius base. And each definition focuses on a different perspective. Okay, so Bronsted-Lowry definition focuses on the transfer of the proton. If something can donate a proton, that's an acid. If something can accept a proton, that's a base. Okay, so there are substances in this world that can both donate and accept protons. Now we have a term for those substances that we call them amphoteric. Water is an example. H2O. Depending on who water is with, water can either donate, well, you got 2 hydrogens attached to oxygen, so water can either donate protons, since oxygen has 2 lone pair of electrons, in the water molecule, oxygen has 2 lone pair of electrons. Water can also accept a lone pair of electrons. So example here, if you have hydrogen iodine, one of the 6 strong acid, when you dissolve that in water, well, in this case, this guy has a stronger ability to donate the hydrogen ion. In this case, the water will have no choice but to take it in. Water starts with as a neutral molecule, and when you take in a proton there, you end up with H3O plus positive charge. So in this case, water is acting as a base. Water is accepting protons. But if you have a sodium fluoride dissolving water, fluoride ion now has a negative charge in there. Okay. Hydrogen, you got a hydrogen on the water molecule there. Fluoride ion is so electronegative, and they will try to grab the hydrogen from water. In this case, water is donating water is donating the proton. So in this case, water is acting as an acid. So water can be viewed as, can act either as an acid or a base. So this is a special, very special property for water there. And that's why acid can dissolve in water, base can also dissolve in water. A very important feature there, amphoteric, that's the term that we use. Something that can act both as an acid and a base. Okay, so what happens if something donates an electron or accept an electron? What happens to the leftover? What happens to the species that result in the either the donation of the electron, hydrogen ion or the acceptance of the hydrogen ion? We use the term conjugate acid and conjugate base to call those species after the transfer of the proton is finished. So conjugate base would be a substance formed by the loss of hydrogen ion from an acid. So if you have an acid give out a proton, what's left is what we call the conjugate base. So an acid, the counterpart of the acid after the donating of the hydrogen ion, the counterpart is called conjugate base. Okay, and then for acid here, if you have water, for example, removal of the hydrogen ion resulting in OH minus. OH minus is what we call the conjugate base of the acid being water in this case. Now, what happens to the base that accept the proton after accepting the proton? So substance formed by the addition of the proton is what we call a conjugate acid. Okay, now, example here, if you have ammonia, ammonia is a base with a lone pair of electrons. If you put a proton to it, you end up with ammonium NH4+. This is your conjugate acid. So keep in mind, conjugate acid and base, and conjugate base and acid, these things comes in pairs. After you give out something, whatever is left, after you give out the proton there, whatever is left is called conjugate base. Now, you start with yourself, and then when you accept the proton, you end up with conjugate acid. Okay, so these things are always come in pairs. So Bronsted-Lowry definition for acid and base basically indicates for every acid there has a conjugate base. Every base has a conjugate acid. Okay, and they all come in pairs. And here in this case, if you try to dissolve ammonia in water, and you end up with ammonium hydroxide. So this is a base, you have its conjugate acid. This is an acid, you have the conjugate base. Okay, solution is slightly basic, or the solution of the ammonia is slightly basic because of the presence of this thing here. Yeah. So the relative strength determines whether you have an acid solution or basic solution. We'll give you the definition of acid solution, acidic solution or basic solution in just a little bit. And so we ask you, now that we know what happens in the Bronsted-Lowry definition there, so we ask you, we need you to be able to identify what we call the conjugate acid or conjugate base there. So what is the conjugate base for HBr? HBr is one of those 6 strong acids there. So what's the conjugate base for it? Definition, the species after you donate the proton. So what, when you give out as HBr, when you give out H+, what's left in there? Br, there has to be a charge. Br